So I'm going to make sure I'm sharing my screen with you guys. So let me go ahead, share the screen. And this is where I am. All right. So I'm going to go back to the slides and make sure to share the slides. And this is where, let's see, maybe this one, PPT. All right, guys. So guys, I would like to introduce another concept of let me go ahead and share again. And maybe I'll do this one. And share. So let's see if I can share again. All right, guys. So another concept of acid and bases is defined by Bronsted. Bronsted concept defines acid as proton donor, which is pretty much the same as Arrhenius concept. But about the bases, Bronsted concept says bases are acceptor of protons. You don't have to produce OH minus, you're acceptor of protons. So if you look at this reaction, this is oxygen, red is oxygen, yellows are hydrogen. So this is water molecule reacting with another water molecule. As you see, this first molecule is accepting a hydrogen ion from the second water molecule. So it's making H3O plus. And what is left from water when it has lost one of its hydrogen ion, that is OH minus. So this reaction is called autoprotolysis of water. That means two water molecules, one of them can act as an acid, the other one can act as a base. They exchange protons together. As a result, they are going to produce hydroxide ion and hydronium ion. As you see, this reaction is an equilibrium reaction. When you see double-sided arrows, you already know you are dealing with an equilibrium. Every equilibrium has an equilibrium constant, which shows how far the reaction goes to the right. Now, equilibrium constant for ionization of water, which is result of hydrogen ion concentration times hydroxide ion concentration. The value of this equilibrium constant at room temperature is 1.0 times 10 to minus 14. And we are going to use this constant to find concentration of these two related to the other one. Another word, if I give you hydrogen ion concentration, you can always calculate hydroxide ion concentration by this equation. And if I go to the next slide, there is a third concept of acid and bases, and that is called Lewis acid and bases. In this concept, we are not talking about protons. We are not talking about hydroxide ion. What we are talking about is about electrons. Electrons decide whether a compound is acid or base. In this concept, we define bases as donor of electron pair. Water is a base because it can donate electron pair. Ammonia is a base because it can donate an electron pair. This is the structure of ammonia. It has one lone pair on nitrogen, which can donate. This is the structure of water, which has got two lone pairs to offer. And O minus 2, of course, it has got oxygens. It has got electrons, which can donate. So in these structures, one molecule is going to give electron. Another molecule brings an empty orbital to accept the electrons. What is resulting from these electron donor and electron acceptor? You form a bond, and we call that bond coordinate bond. I'm going to give you an example on the next slide. Let's look at BF3. Do you see boron has got 3 electrons before reaction? Every fluorine brought 1 single electron. They have overlap. So total number of electrons on boron is 6. So boron does not have complete octet. So do you see boron has got an empty orbital here, which would love to be filled with electron. So it will have 8 electrons. It would be happy. So boron is acceptor of electron pair. And if I react boron with nitrogen, remember we said nitrogen has got 1 lone pair on nitrogen, and it can give these lone pair. So it's going to act as donor of electron, which makes ammonia is a base. Boron is acceptor of electron. Once these electrons are filling the empty orbital on boron, this is what you're going to make. You make a new bond, and the bond is going to be between nitrogen, this bond between nitrogen and boron is result of nitrogen donating electrons and fluorine accepting electrons. So we call this bond coordinate bond. Coordinate bonds are covalent bonds, except for the fact that covalent bond, regular covalent bond, is result of 1 electron coming from each atom to make a bond. These type of coordinate covalent bonds are bonds which are result of sharing electrons, but both electrons are coming from 1 atom. So boron as acceptor of electron pair is an acid. Ammonia as donor of electron pair is a Lewis base, and the product is a coordinated compound. So the good thing about this system, this definition of acid and bases, is the fact that there is no need for proton compounds like BF3, which doesn't have any hydrogen ion. It can be called acid. Compounds like NH3, which doesn't have OH, is donating electron pair, can be a base. All right, so 3 different concepts for definition of acidity. Now, do you remember, again in Chem 2 we said acids are proton donor, and acids can be divided into strong acid and weak acid. Now, what are the strong acids? They are 100% dissociated. They can give off all their hydrogen ion. Those are the strong acids. What are weak acids? Weak acids are donating their hydrogen ion through an equilibrium, so they are never, well, let's say this is the acetic acid. It's a weak acid. If you react this with water, it can give some proton to make hydronium ion, and what is left is acetate anion. But look, this is an equilibrium. That means the reaction never goes 100% to the right. As a result, we call these weak acids. Weak acids are partially dissociated in water. We also said there are strong acids, sodium hydroxide, potassium hydroxide, barium hydroxide, calcium hydroxide. These are strong acids, but weak acids are, the top 4 compounds are strong base. Sodium hydroxide, KOH, barium hydroxide, calcium hydroxide are strong bases. Bases could be weak as well. What are weak bases? They are bases which are partially dissociated in water. Another word, if you add ammonia, you get an equilibrium to make ammonium hydroxide and OH minus. Well, ammonium ion which is ammonium ion and OH minus. Together they make ammonium hydroxide. So do you have to memorize this table? No, this table will be given to you. And by looking up the table, you would know whether you're dealing with a strong acid or weak acid, strong base or weak bases.